You ever stop and think about what a vibrating guitar string, the ripples in a pond, and a beam of sunlight could possibly have in common? I mean, they seem like totally different things, right? But what if I told you they're all playing by the same rule book? Well, let's dive into this master rule of the universe, the wave equation.
So, here's our game plan. We're going to start by finding this hidden pattern in, well, everything. Then we'll break down what a wave actually is. After that, we'll get into the mathematical code itself, see how it shows up everywhere from light to quantum mechanics, and wrap up by talking about what it all tells us about reality itself. All right, first up, the universal rhythm. We're on the hunt for a shared principle, like an underlying beat that connects a whole bunch of things that, on the surface, don't seem connected at all.
Let's go back to that first question. A musical note, a circle spreading out in the water, a ray of light shooting across the cosmos. What in the world could possibly unite them? It's a fantastic puzzle, and it really hints at a much deeper order in nature.
And here's the answer, the star of our show today. They are all, in fact, described by the exact same mathematical logic, the wave equation. This is the universe's rulebook for how disturbances travel, how energy flows, and, how information gets from point A to point B through space and time.
So now that we know what connects them, let's move on. Before we can really truly appreciate the equation, we need to speak the language of waves. We need to get familiar with their basic building blocks. First, we've got amplitude. The easy way to think about this is just the wave's height or its intensity. So for a sound wave, amplitude is its loudness. For a light wave, its brightness. The really key takeaway here is that amplitude is basically a stand-in for the wave's energy. Next up, wavelength. This is just the physical distance from one peak of the wave to the very next one. It's what makes a high-pitched sound different from a low one, or red light different from blue light. It really just defines the physical scale of the wave.
Then there's frequency. Okay, imagine you're standing in one spot just counting how many wave crests pass by you every single second. That's it. That's the frequency. And it's directly tied to energy. Higher frequency means higher energy. That's a huge concept in all of physics.
And finally, we have velocity. This is just how fast the wave's energy is moving along. But here's the really important part. The velocity isn't set by the wave itself. Nope, it's determined by the medium it's traveling through. A wave doesn't have its own speed. The environment it's in tells it how fast to go.
Okay, so we've got the basic vocabulary down. Now it's time to really look under the hood at the engine that's driving all of this, the code of propagation itself.
So, all those things we just talked about, amplitude, frequency, velocity, they're all bundled together in one super compact mathematical statement. It's a thing called a partial differential equation. But don't let the name scare you. All it means is that it describes how something changes in both space and time at the same time. The name's not important, it's the beautiful meaning that matters.
And there it is! In its classic one-dimensional form, on the left side you have the wave's acceleration in time, and on the right, you've got its curvature in space. The equation is just saying that these two things are proportional to each other. That's it. The change in time is linked to the shape in space.
This, right here, translates all that math into a really powerful idea. Distributed causality just means that if you poke the wave over here, it's going to have an effect over there a little bit later. Temporal memory means the wave's shape right now depends on what it was doing a moment ago. And spatial coherence means the whole wave acts like one connected thing, not just a bunch of separate points.
So how do you solve it? Well, this formula shows us the general solution, and it reveals something absolutely incredible. It says that any complex wave, no matter what its shape is really just the sum of two much simpler waves, one moving left and one moving right. This whole idea that you can just add waves together is called superposition, and it's totally fundamental to how they work.
To really get why the wave equation is so special, it helps to compare it to another big one, the Laplace equation. So imagine you're heating a metal plate. The Laplace equation can tell you the final settle-down temperature at every point. It's a snapshot of a balanced static state. The wave equation, though, it's all about the process of change. It's not about the destination. It's about the journey, how the structure evolves through time.
So, we've got this amazingly powerful equation. Let's move on and see just how far its reach extends. This is where we go from abstract math to the actual reality we all live in.
One of its most famous jobs is in electromagnetism. Light, radio waves, X-rays. They're all just self-propagating ripples in electric and magnetic fields, and they're described perfectly by the wave equation.
It's literally how information travels across the empty vacuum of space, totally free of any matter. It's kinda mind-blowing.
But hold on, because it gets even weirder and honestly, more wonderful. In quantum mechanics, the wave isn't a physical thing bobbing up and down. No, it's a wave of probability. It's a field of pure information, of potential, all described by the Schrödinger equation. At the most fundamental level we can see, the universe behaves like a wave.
And sometimes, waves can look like they're standing perfectly still. This happens when two waves going in opposite directions interfere with each other in just the right way. Think about that guitar string again. You get these stable patterns of stored energy, the harmonics and nodes, that create a musical note. It's just a beautiful example of stability popping up out of constant change.
And that brings us to our final section, a map of coherence. Okay, so what does it all mean? What is this one single equation really telling us about the fundamental nature of our universe?
I just love this quote because it really nails the unique personality of a wave. See, other things in physics like heat spreading out, they tend to smooth things out, erase the details. But waves carry information. They have a memory of where they came from, and that allows patterns to travel across insane distances and even return.
And this table is a great way to think about it. You can look at this equation on all these different levels. On a physical level, it's vibrations and fields. Mathematically, it's a specific type of equation. From an information perspective, it's all about signals. And philosophically, well, maybe it suggests that reality itself is just this grand, coherent, oscillating symphony. So we're left with this final, really big thought. The patterns of light hitting our eyes from a distant star are a memory, a message from a cosmic event that happened billions of years ago. The sound of a voice is a memory of a thought turned into vibrating air. So if waves are the universe's mechanism for memory, for carrying information, what's the message? What is the universe trying to tell us?